Welcome to my video on symmetric matrices. So symmetric matrices, to understand symmetric matrices, we have to understand matrix transposes, which is something we've covered in the past, but I'm just going to briefly reiterate over it. So a matrix transpose, say we have the matrix 1, 2, 3, 4. Very imaginative example, I know. The transpose of that would be 1, 3, 2, 4. And what we're simply doing here is we're making the rows of a transpose can be found by looking at the equivalent entry in the columns of A. So a very sort of inaccurate geometrically, but accurate sort of on the page way of thinking about it is you're just rotating these columns 90 degrees anti-clockwise. Now, so what's a symmetric matrix? A symmetric matrix is one that's equal to its transpose. So if A is equal to A transpose, A can be termed symmetric. So obviously the first thing to note here is that to be symmetric, a matrix must be square. Because if a matrix has 2 by 3 columns, it's 2 rows and 3 columns, its transpose will have 3 columns and 2 rows. So if the number of rows and the number of columns are not equal, the transpose will not even be the same dimensions as the original matrix, and the matrix cannot be symmetric. So that's pretty easy. Another easy thing we can point out is that for a matrix, if a matrix is an identity matrix or a diagonal square matrix, it will be symmetric because the only non-zero entries are on the diagonal. And whenever you take the transpose, the element on that diagonal remains in the same position. So identity matrices are symmetric. Non-square matrices are not symmetric. Now, obviously if you have a matrix and its elements, it's quite easy to find its transpose. It's not a complex process. You just take the elements and you put them where they should be. But what can be difficult is when you're not given specifics about the matrix. For instance, a problem my professor gave me recently was, he told me C is a symmetric matrix, right? So C is equal to C transpose. He said, okay, is C multiplied by C transpose symmetric? Now, obviously we don't know what C is, we just know it's symmetric. But because we know it's symmetric, we know that C transpose must be symmetric. Well, why is that? So first of all, if this condition I've written on the Microsoft Paint here is correct, then then C multiplied by C transpose will be symmetric. Well, what can we do here? Because we know that C is equal to C transpose, we can do this. We can kind of swap these. We're not swapping them. We're just saying, well, C is equal to C transpose, so we're going to make C transpose, and C transpose is equal to C, so we're going to make C transpose C. And all of a sudden we have, is C multiplied by C transpose equal to C transpose multiplied by C transpose? And if you transpose each of the elements in this multiplication before multiplication, you end up with C transpose multiplied by C transpose. And C transpose is just C. So you end up with C transpose equals C transpose. So a symmetric matrix multiplied by its own transpose will still be symmetric. Let's try another example. Is the square of a symmetric matrix symmetric? Well, let's think about this. The square of a symmetric matrix, C squared, can just be rewritten as C matrix multiplied by C. So is C squared equal to C multiplied by C transpose? Well, I don't think we have quite enough yet. But we know that C is equal to its own transpose. So if we transpose these elements here, we just get C transpose C transpose. Is that equal to C squared? Well, we know we can convert between C transpose and C because we know that the base matrix I'm not sure that's the right term, the original matrix we're working with, C is symmetric. So we know we can rewrite this as CC, which is equal to C squared. All right, thank you for listening.